Now we're going to start getting into the pre-processing stage of keyword spotting. Pre-processing is a term we typically use to refer to the set of tasks that we perform right before we do inference. Now, this is the part of the main loop and not part of the initialization. So focusing on the main loop, here you see the pre-processing contains two steps. First is the audio provider, and the second is the feature extractor. The job of the audio provider is really to deal with setting up the microphone to get the audio input from an analog into a digital representation. If you remember in part 2, we briefly talked about how to get an audio signal from a continuous signal, which we sample at about 16 kilohertz, that we then convert into a digital representation. Now, all of this A to D, is analog to digital conversion is done by libraries that we are piggybacking, that come equipped with the Arduino. So the first step that we actually have to configure the Arduino's microphone, and there's a very simple function that we have written that does exactly that. For now, you just need to know that there is a function that actually sets up the microphone, and that's the key takeaway. Typically, this function ends up being quite dependent upon the device. So for example, if you're using a SparkFun Edge 2 or a HiMax board, then you're going to have to rewrite these functions to be quite specific to that particular platform. Keep that in mind as you try and extend outside the scope of things that we are covering here. So the audio provider's next job is that once the microphone has been configured to set up a certain sampling rate, it's got to continuously read in the analog voltage signals that are coming in through the microphone and get a digital representation and dump that representation into an audio buffer. And that is a process that is repeated continuously because we need to continuously be sampling the audio signals to know when the user may have said a keyword. Now, the way we do that is by having this particular get audio samples function here. This function captures and populates the actual audio samples into a buffer that is going to store the audio signals as 16-bit values inside each and every single one of those entries. Once you have that audio buffer, we have captured the raw digital samples of the audio signal. What we need to do is extract features from that. Now, if you remember in part 2, one of the key things that we said is that we take a continuous signal, we convert the continuous waveform into a spectrogram, something that a neural network can easily ingest and process as a convolutional neural network can for a given image. And out of that spectrogram is how we actually infer whether we actually have a certain keyword that's being spoken. Fairly simple. So how do we exactly do this? Well, in the implementation, we take a 30 millisecond clip, and that's one snapshot. And out of that one snapshot, we generate as an FFT. The FFT, recall, is a much more effective representation of a time series signal in the frequency domain. And we get 256 values out of that. And in order to make the FFT more representative and robust, we end up doing averaging, which then leaves us with 43 unique values. And these 43 unique values are effectively one slice of the spectrogram that we have. And we end up doing, after this, we get one slice, then we shift the red box, as you have seen on the little screen in a bit. And then there's a second time step effectively. And these dotted lines on the waveform are a new set of recordings, and we're going to be pulling in. So one of the key things to notice in the figure, that we have right now is to look at the overlap between the solid red box and the dotted red box. And what you will realize here is that there's a sliding window of 20 milliseconds. Now, remember, I said that the box itself is 30 milliseconds, which means that if I slide it over by just 20 milliseconds, that means I'm going to have about 10 millisecond worth of data still from the past. And that's a good thing because you want to have some sort of overlapping features. And that's what I want to capture here. And then we continue this process effectively until we end up filling the spectrogram. And this behavior is actually handled by the feature provider. And the feature provider's job, which we defined earlier in the initialization stage, which then in a loop stage continues to repeat over and over, is to actually fill the buffer up. So it's doing this is getting audio samples, waiting for the buffer to actually replenish itself all the way to a full 1 second worth of data. And once we have 1 second worth of the actual spectrogram data in there, then we can actually do an inference. So the way things are tying up is that you've actually got this audio signal. The audio signal is actually a time domain signal, which we have converted into a frequency domain. Okay, we know how that is done now. And from that frequency domain, what we do is additional optimizations. If you remember in course of the part 2, we talked about how we do MFCCs using the MEL filter banks. MFCCs really simply is the fact that our ear naturally picks up low frequency signals much better than higher frequency signals. And therefore, if we focus our efforts more on low frequency signals, then we are likely to pick up the words much better. So what the bottom spectrograms are showing is like what happens when you take a regular spectrogram and then you convert it with an MFCC. It emphasizes the lower frequencies much more cleanly, and that allows our machine learning model to pick up those signals for those keywords also much more cleanly. Now, one thing I want you to keep in mind is that this process, might vary depending on the capabilities of your microcontroller. For example, if you have a very powerful microcontroller, you might choose to run, a much more complicated, a much more precise FFT, and a much more sophisticated MFCC method. But if your microcontroller is like ours, that's rather simple and very power constrained, then you might not have the flexibility to do this kind of computational in terms, for this kind of application. So in this case, you might choose to implement something quite simple for your FFT and MFCC, which is something that we will do in our TensorFlow Lite micro example for micro speech. So all of this generating features is going all the way from audio signal to the spectrogram. It's actually done by this function called generate micro features. And we'll look at that code that's involved in the generate micro features later on in the tutorial. But for now, conceptualize that this is the function that you should focus on for spectrogram generation aspects. This basically is taking audio signals and generating spectrograms for us. Super simple. Now, to take a step back, this is effectively the keyword spotting's pre-processing nugget. You've got the audio provider, which knows how to take the audio signals from the microphone and then convert them into a digital representation. Then you've got the feature extractor who takes the digital representation and converts them into the spectrogram. And this is the pre-processing that happens before we call the keyword spotting's inference, which is effectively invoking the tiny corn model, which I'll talk to you about next.